most surprising offshoots of geometric sum equations is the revelation that you can add an infinite number of terms. And for an example, let's say I'm standing on a table and I'm going to jump off the table and hit the floor. Or in other words, I'm going to fall 1 meter to the ground. The question is, do I hit the floor? Duh. Of course you hit the floor, right? Or do you? Think of that 1 meter as a number line, and do you agree that I would have to fall half of a meter? Yes. Do you agree that I would have to go half of that meter? And do you agree that I'd have to go half of that meter? And half, and half, and half. How many of those half of a meters would I have to go? And the answer is an infinite, right? An infinite number of halves. So if I'm writing this as a series, it would be 0.5 plus 0.25 plus 0.125 plus on you go, 1/2 to the n. So my question is this equal to 1? Is it equal to 1? You think it is. It seems like it should be. But think of this number line as a pie. Okay? You eat half of the pie. Then you eat half of the half pie. Half, half, half pie. Half, half, half pie. Half, half, half pie. And you just keep half, half, half. You just keep doing this. And then hopefully, what happens by the end? By the end, we think you will have eaten the whole pie. So the question is, does an infinite number of terms add up to a sum? And you would think there's no way. And the Greeks definitely felt that it did not. But let's look at some patterns here. If I took 1/2 plus 1/4 plus 1/8 on into infinity, this is actually going to add up to 1. 1/3 plus 1/3 squared plus 1/3 cubed, this is going to add up to 1/2. 1/5 plus 1/5 squared plus 1/5 cubed will add up to 1/4. Could you figure out what 1/9 plus 1/9 squared plus 1/9 cubed? Or maybe these two. Could you figure these two out? Well, we're going to be able to do that with our formula. For the sum of an infinite number of terms, what if this n goes to infinity, but the ratio is less than 1? For example, what is 1 over infinity? Well, 1 over infinity, that's just going to be 0, isn't it? We saw that before. So 1 over 2 to the infinity is the same as 1 over 2 to the infinity. And what's 1 over 2 to the infinity? That's going to be 0. So what we're saying here is that if your ratio is less than 1, and we could say less than 1 and greater than -1, we just simplify it with absolute value. What happens is that this r to the n goes to 0. So our formula becomes much simpler. It just becomes a times 1 minus 0, or a over 1 minus r, giving you one of the most beautifully simple formulas dealing with infinite number of things that I've ever seen. There's 2 rules to it, though. It has to be a geometric series. And the other is the ratio has to be less than 1. If those 2 rules aren't met, it doesn't work. Welcome to advanced math. Advanced math will have formulas that only work under certain conditions. And it's great that you can use this formula, but it doesn't work all the time. It only works under certain conditions. So look at this one. We have 2 plus 2/3, 2/9. Well, the first term is A, which is 2. The ratio, what I'm multiplying by each time, needs to be less than 1, and it looks like I'm multiplying by 1/3. Is that less than 1? Absolutely. So therefore, my ratio is 1/3. We should be able to use this formula. Yes. Sum to infinity will be A over 1 minus R, or in this case, 2 over 1 minus 1/3, which is 2 over 2/3, which is 3. This adds up to 3. Isn't that neat? That is the greatest. You got an infinite number of terms. You start with 2, and the sum adds up to 3. Crazy. Crazy. Okay? So there's your formula. One more time. Has to be geometric. Has to have a ratio less than 1 or greater than -1. And so we would check that before we even try to use this formula. So this one here, it looks like we're multiplying by 1/3. Multiplying each time means geometric. Its ratio is less than 1. Yes. This one, we're multiplying by 3. It is geometric, but the ratio is greater than 1. So this would be a no. 4 to 1, we're multiplying by, it looks like -1/4. Each time. And that ratio is less than 1 or greater than -1, and it's geometric, so that one's going to work great. This one, it looks like we're multiplying by 5, right? -5 each time. It is geometric, but it is not the right ratio, so we would say no to that one. So first, double check to make sure you can do it, and then go ahead and find those. And that's infinite geometric series. I'm going to do one of your problems because I think this shows why this is such a great formula. A swinging pendulum covers 32 centimeters the first swing, 24 the second swing, 18 the third, and it goes to infinity. Okay? Eventually, I think that swing is going to be 0 because it's going to stop, isn't it? Well, the first thing you want to do is to see what ratio you have. So 24 over 32 is the same as divided by 8, 3/4. 18 over 24 divided by 6, you're going to get 3/4. So since those ratios are the same, ratio is 3/4, it is geometric. It has a ratio less than 1. So we can use the formula. Sum to infinity, A over 1 minus R. So A is the first term, 32, over 1 minus the ratio, which is 3/4. You'll like this. This is going to be 32 over 1/4, which is 32 times 4, which is 128 centimeters. That is the total swing of the pendulum. Isn't that awesome? That's just so cool. So the only other thing we need to look at is repeated decimals. I just wanted to let you know there's a notation thing when you see 2 dots above, connect the dots, and you can see that this is the same as 23 hundredths plus 23 10,000ths. The next one will be 23 millionths And so you can figure out what the ratio is. The first term, of course, is A. The ratio is 1 over 100 each time. So we definitely can use that. So my suggestion is to start by listing the terms. This will be 3 plus 1/10 plus 1 100th plus 1 1,000th to infinity. Find this sum and add 3. So get your A term and then get your ratio. Shouldn't be a problem. This one here is going to be 2/10 plus 35 over 1,000. Then it repeats 35 over 100,000. 35 over, I think it's 10 million. And you can find your R and find your A for each. And then find that formula. Double check to make sure the ratio is less than 1. All right, so you are ready to work on the infinite sums. Find R, find A, see if it's geometric, see if the ratio is less than 1, greater than -1, and you're good to go.